In solving these linear problems, we're going to have a homogeneous part and a particular part once again. We're going to start with the homogeneous solution. So on the left is the homogeneous second order equation. On the right is our system equivalent in first order. So we use information from the system side on the right to deduce things about the original problem on the left. First of all, observe that if we're going to have an initial value problem for the system, that means we would be given an initial condition on the vector u. That implies for the second order equation on the left that if we want to impose an initial condition on that problem, it'll have to be a condition on x and on x prime. So in the second order scalar problem, we need two initial conditions to get a unique solution. To find solutions of the system, we need to find the eigenvalues of this companion matrix, which means we need to find the roots of the characteristic polynomial. As always, we get that as the determinant of A minus lambda times the identity. The result is just lambda squared plus b lambda plus c. Well, we might as well call that the characteristic polynomial for the original problem as well. We can actually skip all the intermediate stuff because it's very obvious how that polynomial relates to the original second order equation. Now we know we have to draw a distinction between whether the eigenvalues are two different values, two distinct values, or whether they are a double eigenvalue. If we look at the quadratic formula, then we can see that we get a double root when b squared equals 4c. In that case of a double root, the matrix is definitely not diagonal unless b and c are both 0, in which case the problem is completely trivial. So that means it's going to be defective. And we'll have to consider that situation separately. First, let's deal with the non-defective case. Two distinct eigenvalues. We have to find eigenvectors, which we do by looking at the matrix A minus lambda I. If we swap the entries of the first row and put a negative on the lambda, then we just find that the eigenvector is 1 lambda. In system terms, the general solution is a combination of e to the lambda 1t times v1 and e to the lambda 2t times v2. But in the original scalar second order equation, remember the conversion is that u is x and x prime, so we really only want u1 as our solution, the first component. And then it becomes really easy. It's just a combination of e to the lambda 1t and e to the lambda 2t. So again, we can skip a lot of intermediate work. All we need are the roots of the characteristic equation, and we can write down the solution right away. In the real case, that's really all there is to say. When the roots are complex, we need to get a little bit more into the weeds. So let's say the eigenvalues are alpha plus and minus I beta. Well, if we have a real solution, then it works out that the C2 in that formula above is the conjugate of C1. And then if you're adding something to its conjugate, you're really taking the real part. I'm going to absorb the factor of 2 into the constant. So we could just take the real part of c1 e to the lambda 1t, and e to the alpha t is real, so that can come through. So that's one form of writing the general solution. We'd have the real and imaginary parts of C1 as arbitrary constants. Equivalently, we can take the real and imaginary parts of e to the lambda t and get two independent real solutions, and we can use those to construct the general solution. We've seen these two things before. There is a third way that's very convenient sometimes, and that's to write a single cosine with a phase shift and then an amplitude out in front. We call this phase amplitude form. All three of these methods are equivalent. All three of them have two arbitrary real constants to be determined. In order to connect that third case to the second case, we could use this simple trig identity for the cosine of a difference. And then equation 3 equals equation 2, provided we define A1 as r cosine theta and A2 as r sine theta. But that's particularly memorable. It's the same thing as when we do polar coordinates. So if you think of A1, A2 as a point in regular coordinates, then you convert that to polar and you get the r and the theta. Some quick examples. The characteristic polynomial here, you just use the derivatives on x as the power of lambda. That factors into two real roots. So the solution is a combination of e to the minus 2t and e to the minus 3t. Here's another case. Polynomial is lambda squared minus 2 lambda. There's no constant term because there's no pure x term. Well, that has roots 0 and 2. So you get c1 e to the 0t plus c2 e to the 2t. Third case. Our formulas are written assuming a leading coefficient of 1 on x double prime. So I'll divide through by the 3. Characteristic polynomial is lambda squared plus 2 lambda plus 10. On this I'll use the quadratic formula. Square root of 36 is 6, so we just get minus 1 plus or minus 3i. So we have our three forms. The real part of a complex constant times e to the lambda t, or combination of e to the alpha t cosine beta t and e to the alpha t sine beta t. Remember, alpha plus beta I is the expression of the eigenvalue. Or we can use an amplitude times e to the minus t times cosine of 3t with a phase shift. Now to produce the solution in the defective case. This occurs again when b squared equals 4c, and then the double root is negative b over 2. We take the same tactic as we did in the defective case before. We'll shift b by a multiple of the identity. and we'll apply the fact that c is equal to b squared over 4. Well, if we find b squared, capital B squared, the 1, 1 entry is b squared over 4 minus b squared over 4. The 1, 2 entry is b over 2 minus b over 2. All of them work out to be 0. So all the higher powers of capital B will be 0 as well. So the exponential series for e to the tb has just 2 terms. And then to get the exponential of a, we just multiply that by e to the negative bt over 2. The general solution in system terms is e to the ta times an arbitrary vector c. But for the original second order problem, we only need the first component of that. And that simplifies the algebra somewhat. I'm going to rename the constants c1 and c2, and then we can write the whole thing as e to the minus tb over 2 times a c1 plus c2t. That's all we need in the defective case. And it's even easier than it looks because negative b over 2 is the eigenvalue, which we compute first thing anyway. Example, characteristic polynomial is lambda squared minus 4 lambda plus 4, which is a perfect square. So 2 is a double root. That means I need e to the 2t, and then times a c1 plus c2t.